Welcome, everyone, to another deep dive.
Okay.
Today, we're kicking off something a bit special. It's our CSWIP 3.1 exam prep series.
Yeah, we designed this specifically to help aspiring welding inspectors like you listening really sharpen your knowledge for that crucial CSWIP 3.1 certification. Our mission here is simple. Cut through the noise, tackle some really critical concepts by breaking down multi-choice questions. Think of it like a guided tour. We want to help you grab knowledge quickly, but, thoroughly. Sidestep that feeling of being overwhelmed with info and hopefully land those really satisfying aha moments.
Yeah, absolutely. And, passing the exam, it's not just about memorizing option A, B, C, or D. It's really about deeply understanding the why behind each answer. That's where the real value is. And honestly, that's what's going to make you an effective, confident inspector out there in the field. So yeah, we're here to guide you through a practical, insightful look at welding principles, one question at a time. Perfect. All right, let's dive straight in then with our first challenge, okay? Carbon equivalent values, or CEV, are used to determine how to avoid the risk of. Which of these is it? A, hydrogen cracking, B, Lemel pairing, C, solidification cracking, or D, weld decay? Take a second, think about that one.
Okay, the correct answer here is A, hydrogen cracking.
Hydrogen cracking. Right. Now, that's a term that definitely gets attention. Some people might think it's just about moisture, keeping things clean during welding. But CEV, that really brings the metallurgy, the material itself, right into focus, doesn't it? So what's the fundamental link here? Why is the materials chemistry so critical for this specific type of crack?
That's a great point. It's not always immediately obvious. Think of CEV as a kind of hardenability score for the steel. It's a calculated value, right? It tells you how easily that particular steel will form, brittle structures when it cools down after welding. Mm-hmm. The higher the CEV, essentially, the more alloying elements are in there, and the higher its hardenability. This means it's much more prone to forming very hard and, unfortunately, very brittle microstructures, like martensite. In the heat-affected zone, the HAZ, as it cools.
Martensite, right? A very hard needle-like structure.
Exactly. Super hard but brittle. And it forms when steel cools really quickly from high temperatures, so it's susceptible to failure. Now, add hydrogen into that mix. Hydrogen can come from moisture in your electrodes, your flux, even just the air around you. That hydrogen gets trapped, sort of diffuses into the weld metal, and especially into these new brittle HAZ structures. And those brittle zones, they become prime spots for hydrogen embrittlement. The hydrogen basically makes the steel even weaker, more brittle. And that's where the cracks start. Often delayed cracking, too. Sometimes hours, even days after the weld looks perfectly fine.
Wow. Okay, so for you listening, the inspector, understanding CEV is almost like having an early warning system then. It tells you straight away what precautions, like maybe preheating before you even start welding or doing a post-weld heat treatment afterwards. It signals those might be absolutely necessary to dodge those potential cracking headaches. It's a critical preventative tool, really.
Precisely. It guides your approach.
Okay, that insight into the material science is just, fundamental. Now, let's maybe shift gears a bit from the steel's inherent properties to how we actually manipulate things during the welding itself. Because even with the right material, the way we weld introduces its own set of challenges. Our next question gets into adjusting parameters in submerged arc welding, or SAW doubly. So for SAW, what is the effect of raising arc voltage, but keeping all other parameters the same? Your options: A, weld bead width will increase, B, depth of penetration will increase, C, weld bead width will decrease, or D, depth of penetration will decrease. What happens when you turn up the voltage?
Okay. For this one, the correct answer is A, weld bead width will increase.
Right. Now this is where it gets really interesting with submerged arc, because I think intuitively you might think more voltage, more power, deeper penetration, But here we're seeing a wider, often shallower bead. Why does that happen? What's the physics behind SAW behaving like that?
Yeah, that's a really common assumption, and it's a great question because it shows how different processes react differently. In SAW specifically, the arc voltage primarily controls the arc length. So when you increase the voltage, you're making the arc physically longer between the lectured tip and the workpiece.
Okay, longer arc.
Yeah, and a longer arc is, less constricted. It has more room to spread out sideways, so this wider arc spreads the heat over a bigger area on the base metal. And the results of that, a wider, flatter weld bead. And because that energy is spread out, less of it is focused downwards, digging deep. So the penetration depth often decreases, or at best doesn't really increase much.
Right, the energy density drops.
Exactly. If you actually want more penetration in SAW, the main thing you adjust isn't voltage, it's the welding current. Amperage is key for penetration there.
Okay, so if you're out on a job, maybe inspecting or even troubleshooting, and you see a saw bead that's too narrow, maybe not wetting out well at the toes, your first thought might be, let's look at the voltage setting. That knowledge really helps you diagnose SAW issues on site, doesn't it? Take some guesswork out.
Absolutely. It directs your investigation.
So precise control is vital. But okay, what happens if we go the other way? Maybe we're putting in too much heat. Our third question looks at this. Welds made with very high heat input will show a reduction in what? Either A, tensile ductility, B, notch toughness, C, fatigue strength, or D, creep resistance. Think about the potential downsides of excessive heat.
Right. And the correct answer here, which can sometimes surprise people, is B, notch toughness.
Notch toughness. Okay, that term might not be front of mind for everyone, but it's incredibly important for structural integrity, isn't it? Especially in tough conditions. And hearing that high heat input actually reduces it. Well, it feels a bit backward. You think more heat, stronger welds, maybe. But you're saying it actually makes it more brittle where it matters most. Can you unpack notch toughness for us and why too much heat harms it?
Yeah, happy to. Notch toughness basically describes how well a material can absorb energy, especially impact energy, when there's a stress concentrator present. Think of a sharp corner, a small defect, basically a notch. It's the material's resistance to brittle fracture starting from that point. Critical for preventing catastrophic failure, especially under impact or at low temperatures.
Okay, resistance to brittle fracture.
Exactly. Now, the counterintuitive part. Excessive heat input during welding actually leads to a slower cooling rate for the weld and the HAZ. And that slow cooling gives the metal atoms more time to arrange themselves into larger, coarser grain structures.
Bigger grains.
Bigger grains. And generally speaking, coarser grains are less effective at stopping a crack from propagating. They reduce the material's ability to deform plastically and absorb energy before it snaps, so they're inherently less resistant to brittle failure. Makes the weld more vulnerable if it gets hit hard or has a stress riser.
So it really is a delicate balance then. Too hot is just as bad in some ways as too cold or too little input. That's a vital concept for you listening, especially when you're inspecting critical parts that need to handle dynamic loads or maybe operate in the cold. It's about the microstructure, not just melting metal.
Precisely. Controlling that microstructure is key.
Okay, speaking of delicate balances, let's hone in on MIG-MAG welding now, another workhorse process, but with its own particular quirks. Question 4. MIG-MAG welding has a tendency to give lack of sidewall fusion when which condition is met? A, spray transfer conditions are used. B, 100% CO2 shielding gas is used. C, pulse current is used. Or D, dip transfer. Which transfer mode is the usual suspect here?
Right. For this one, the answer we're looking for is D, dip transfer.
Dip transfer. Yeah, that's a really critical point for MIG-MAG, isn't it? The transfer mode isn't just about how fast you weld. It directly impacts the kinds of defects you might get. And lack of sidewall fusion. Well, nobody wants that. Why is dip transfer specifically so often linked to this problem?
Yeah, it's a classic process defect relationship. In dip transfer, some call it short circuit transfer, a wire actually, physically touches the weld pool repeatedly. It shorts out, melts off a droplet, the arc reignites and repeats.
Okay, that constant dipping.
Right. And that whole process generates a relatively cool and quite narrow arc compared to spray or pulse transfer. Because the heat input per cycle is lower and the arc isn't as, let's say, forceful, it often just struggles to generate enough heat to properly melt and fuse into the sidewalls of the joint, especially if you've got a narrow V-prep or you're welding thicker material.
Like trying to melt the edges of a thick steak with a small candle?
Kind of, yeah. It just doesn't have the oomph or the reach. Compare that to spray or pulse transfer, where you've got higher, more consistent heat and a more driving arc. Dip transfer is just inherently more prone to leaving those little unfused areas right along the joint edges. A nasty defect.
Yeah, definitely. This really underlines how important it is to pick the right transfer mode for this specific application. And for you, the inspector, knowing these tendencies helps you predict where problems might pop up or figure out why you're seeing that lack of fusion during an inspection. That link between defect and process parameter is gold.
It is. It helps you ask the right questions.
Okay, so we've navigated material chemistry, arc physics, transfer modes. Now let's talk about what happens after the welding's done. specifically post-weld heat treatment, or PWHT. Final question for today. During PWHT of a complex fabrication, it is heated to the soak temperature at a much faster rate than specified by the procedure. This may, what, cause excessive oxidation, B, not allow sufficient time to relieve stresses, C, introduce excessive compressive stresses, or D, cause distortion.
All right, the correct answer for this last one is D, cause distortion.
Distortion, right? And on complex fabrications, things with lots of different shapes, thick sections, bolted to thin sections, distortion can be an absolute nightmare, huge cost implications. But some might think, well, as long as it gets to the right soak temperature eventually and stays there long enough, does the speed of getting there really matter that much? What's the hidden danger in heating up too fast?
That's a very practical question, and it really hits on thermal management. Reaching the soak temp and holding it is vital, yes, but how you get there is just as crucial, especially with complex parts. These fabrications often have, big differences in thickness and geometry all clamped together. When you heat them too quickly, the thin parts heat up fast and want to expand, while the thick, chunky parts lag behind, still relatively cool and resisting expansion.
Creates internal stress.
Exactly. You get significant temperature differences, thermal gradients across the whole thing. This uneven expansion creates localized stresses. And at those high PWHT temperatures, the material's yield strength is lower. So these stresses can easily exceed the material's strength at that temperature, leading to permanent yielding, permanent deformation, which we see as distortion.
Ah, okay. It literally pulls itself out of shape.
Pretty much. That's why controlled, gradual heating rates are specified in procedures. They're critical to allow the temperature to equalize slowly throughout the structure, minimizing those damaging differential stresses and preventing the part from warping. It needs time to adjust uniformly.
That's a brilliant explanation, and connecting that back, it really shows that every single step matters, doesn't it? From choosing the material to the welding parameters right through to the heat treatment. For you inspecting these big, complex jobs, understanding that entire process, the whole life cycle, is essential to catch potential problems and, frankly, avoid incredibly costly mistakes and rework.
Couldn't agree more. It's all connected.
And that brings us to the end of this deep dive into these key CSWIP 3.1 concepts for today. Wow, we've covered quite a bit from the chemistry of CEV, the physics of saw voltage, that counterintuitive effect of heat input on toughness, MIG transfer modes, and the crucial control needed in PWHT. Understanding these principles, the material science, the process details, the post-weld stuff, it isn't just about ticking boxes on an exam. It's about building that solid foundation that makes you a genuinely competent, effective welding inspector out there. Really getting the why is your key to solving problems and ensuring quality.
Absolutely. And maybe just one final thought to leave you with as you continue studying and observing. Think about how all these factors we discussed, material properties, those process parameters, the post-weld ops, they don't exist in separate boxes. They're constantly interacting, influencing each other. So ask yourself, how might changing just one thing, like the heat input, ripple through and maybe affect the risk of cracking and the final toughness and maybe even distortion later on? Keep that curiosity going. Keep observing critically. It's how you'll really grow as an inspector.
That's a fantastic point to end on, that interconnectedness. Thank you for joining us on this special deep dive. We really hope this has helped clarify some things and given you some solid takeaways. Until next time, keep digging deeper.